All right, in this video, I'm going to overview the background sections of Lab 7. Now, this lab is a little background heavy, but once we get through the background sections, the procedure is relatively straightforward. There are 4 background sections. In section A, I'll overview the Doppler effect. In section B, I'll overview the 21 centimeter emission line, which we'll use to measure Doppler shifts. In section C, I'll overview the rotation curve of our Milky Way galaxy in 2 parts. In part 1, I'll describe the radio spectra that we'll collect with our radio telescope. And in part 2, I'll describe how we'll use these spectra to measure radial distances and orbital speeds, which together gives us the rotation curve. And then in section D, I'll overview the radial mass distribution of our Milky Way galaxy and how to measure it from the rotation curve. Okay, let's go into background section A on the Doppler effect. To understand the Doppler effect, first consider a source that's stationary with respect to observers on either side of it. And suppose the source is emitting light of a particular wavelength, where the blue circles correspond to the crests of that wave. This circle corresponds to the crest that was emitted at time 1, this circle to the crest that was emitted at time 2, time 3, time 4, and another crest is being emitted now at time 5. If the source is stationary with respect to the observers, or the observer is stationary with respect to the source, then the observer will measure the same wavelength, the same distance between crests as was emitted by the source, whether on this side or on this side. But if the source is moving with respect to the observers, or the observer is moving with respect to the source, it's a different story. Here we see the crest that was emitted at time 1 when the source was at this location. Here we see the crest that was emitted at time 2 when the source was at this different location, the crest that was emitted at time 3 when the source was here, and the crest that was emitted at time 4 when the source was here. So as you can see, the crests get compressed in the direction of motion, and they get stretched out in the opposite direction. So this observer will measure a shorter wavelength, a shorter distance between crests than was emitted by the source, and this observer will measure a longer wavelength than was emitted by the source. How much shorter and how much longer is given by these equations. If the source is moving towards the observer, the observed wavelength is equal to the emitted wavelength minus the change in wavelength. The source is moving away from the observer, the observed wavelength is equal to the emitted wavelength plus the change in wavelength, where the change in wavelength is given by this equation, the Doppler shift equation, and that is equal to the emitted wavelength times the component of the source's motion that lies along the line of sight, delta V, divided by the wave's speed, which in this case is the speed of light. Delta V is very important. It's the component of the source's total motion that lies along the line of sight. In these examples, it's a simplified case where the source is moving directly towards the observer or directly away from the observer. But in general, the source can be moving in any particular direction, as we see here, in which case delta V is the component of this total motion that lies along the line of sight between the source and the observer. This is an important distinction that we'll make use of in the sections to come. But now let's go into background section B on the 21 centimeter emission line. So here we're looking at a visible light picture of the plane of our Milky Way galaxy in galactic coordinates. The galactic center is here, and the plane is horizontal about it. Now, if we want to study the motion of our Milky Way galaxy, we need to peer into this plane. And at visible wavelengths, there's a problem, and that problem is dust. Dust is blocking our view. We see some of it here. These dark lanes are dust lanes. There's clouds of gas with a lot of dust in them, blocking whatever lies behind it. And the parts that we do see, that's relatively nearby, because the parts that are farther away are blocked by dust that's deeper into this distribution. So this is just something we can't do at visible wavelengths. We can't probe the entire galaxy, just light that's relatively nearby. It's not blocked by dust. To get around this problem, we need to look at a different wavelength. We need to look at a wavelength that is bigger than the grains of dust. And we can do this in the radio. Radio waves are larger than the grains of dust, and so they essentially go right through them as if the dust isn't even there. So all that we need is an emission line, some process that will produce line emission in the radio that we can measure Doppler shifts of. Now, when you think of emission lines, you normally think of atomic transitions, an electron jumping from a higher level down to a lower level. But this makes much higher energy light. It makes visible light or infrared light or ultraviolet light, most of which gets blocked by dust. Transitions in the radio occur differently. We're going to make use of something called the spin-flip transition of cold neutral hydrogen, which produces an emission line at a wavelength of 21 centimeters. That it comes from cold neutral hydrogen is great because the galaxy is composed primarily of cold neutral hydrogen. Let's take a look at the emission mechanism. This occurs completely in the ground state. The electron remains in the ground state the entire time. It's made possible because the proton and the electron act as little magnets. They're both charged and they're both spinning. Whenever you have charge spinning, you get a magnetic field. So the proton and the electron act as little bar magnets. And you've played with bar magnets before. There's a configuration that takes less energy to hold them together when they're oppositely aligned, and a configuration that takes more energy to hold them together when they're aligned. So within the ground state, we have two energy level possibilities: a higher energy state where the two little magnets are aligned, and a lower energy state where they're oppositely aligned. Consider an atom in the lower energy state, a simple hydrogen atom floating in a cloud of gas. Occasionally, it will get jostled. Another atom will bump into it and transfer some of that energy of motion, some of that energy from the collision to the electron, and the electron will transition into the higher energy state. We call that collisional excitation. Then, after a certain amount of time, a random long amount of time, the electron will automatically transition back down to the lower energy state, releasing the difference in energy. And it's a small difference in energy corresponding to a 21 centimeter photon. And that's where the emission line comes from. Now, the typical time scale for this transition to occur randomly on its own is about 11 million years. And given that, you may think, well, we won't see much of this. But cold neutral hydrogen is so abundant that despite that long time scale to transition, we still get a whopping strong signature. So let's take a look at this map here. This is a map of the entire sky in galactic coordinates. So the galactic center is at the center of the map, and here we have the plane of the galaxy. And this map was made at 21 centimeters. It's a map of the 21 centimeter emission line. So this is showing us where the cold neutral hydrogen is in our galaxy. And this is what we'll make use of in the next section. Now, let's consider what the spectra will look like acquired at different locations along the plane of our galaxy at different galactic longitudes. And let's begin by considering what the spectrum will look like if we point our telescope directly at the center of our Milky Way galaxy. For that, consider this top-down map of the Milky Way. Now, we've never been able to send a spacecraft far enough out that we could turn around and take a picture like this. Not by a long shot. These distances are just far too great. So how did we get a picture like this? This was reconstructed using the exact same types of radio spectra that you're going to acquire in this lab. It's accurate to maybe the 10 to 20% level, but certainly good enough for us to visualize what these lines of sight look like and what the spectra that we will acquire should look like. So here we have the center of the galaxy. Here we have the sun's location, our solar system, and one of the arms in the outskirts. And here we have the line of sight from us through the center of the galaxy and across it. I've added a red arrow at every location where the line of sight intersects an arm of the galaxy. And the direction of the arrow shows you the direction that these regions are traveling about the center of the galaxy. When we're looking directly at the center of the galaxy, all these regions of intersection are either moving to our left or to our right. None of them have any component of motion towards us or away from us. So none of this emission should be blue shifted or red shifted. We should just see a single emission line around 21 centimeters. So when you take this spectrum, this is what you'll see. You will see a broad emission line, but there are some extras in this spectrum only. And that's because when we're looking at the galactic center, we're not just looking at the cold neutral hydrogen along that line of sight, but we're looking at Sagittarius A star, which is the radio emitting region about the supermassive black hole, the center of our galaxy. And some of that extra radio light is being absorbed on its way to us by the exact same cold neutral hydrogen. So we do see an emission line, but superimposed on top of it, we see a narrower absorption line. Again, we'll only see that along this line of sight. In fact, we see a second absorption line, which corresponds to a cloud, cold hydrogen gas between Sagittarius A star at the center and us. And this cloud must be moving towards us because it's producing a blue shifted absorption line. Anyway, let's consider a different line of sight, not directed at the galactic center, but off to the side. And here's the corresponding top-down map. Here's the sun. Here's the line of sight. And again, I've added an arrow at each point where the line of sight intersects an arm of the galaxy. And the direction of each of these arrows indicates that region's direction of motion about the center of the galaxy. What's different this time is that each of these arrows has some component of motion along the line of sight, which means the emission that we receive from each of these regions will be red shifted or blue shifted. So here's what that spectrum looks like along that line of sight. And instead of seeing a single emission line, we see 1, 2, 3 emission lines corresponding to 3 separate arms of the galaxy. And the rightmost one, the most redshifted one, is special. That corresponds to this point right here, where its motion is completely along the line of sight. And this is a very useful point because it forms a right angle with the center of the galaxy and with us. And that makes it very easy to calculate its distance from the center of the galaxy and its speed orbiting the galaxy. If we do this for a variety of lines of sight, collecting a variety of these special points, we can figure out the galactic rotation curve, how the speed at which material orbits the galaxy changes as a function of its distance from the center of the galaxy. Let's begin by measuring distances. In the previous lab, we measured the distance between the Sun and the center of the galaxy, and it was approximately 8.1 kiloparsecs. That's the length of the hypotenuse of this triangle. This angle here is the galactic longitude of this particular line of sight. Consequently, this side of the triangle, the distance of our special region from the center of the galaxy, is 8.1 kiloparsecs times the sine of the galactic longitude. Now, if you didn't have trigonometry, don't worry. You can treat this simply as a button on your calculator. Now, if you're using your calculator, make sure it's in degrees mode. If you're instead calculating this with a spreadsheet, you'll need to convert from degrees to radians before applying the sine function. But in the end, you'll get the distance of the special region from the center of the galaxy. So now all that we have to figure out is its speed along this line of sight. That's its speed orbiting the center of the galaxy. We do this in 2 parts. First, we calculate its speed relative to us, and then we add that to our speed, or the component of our speed, along this line of sight. First, the speed of this region relative to us is given by the Doppler shift equation, which we discussed above, and it's repeated here. The relative velocity is equal to the speed of light times the change in wavelength divided by the emitted wavelength, where the change in wavelength is equal to the observed wavelength of the most redshifted component corresponding to this special region minus the emitted wavelength. And the emitted wavelength of cold neutral hydrogen is 21.1061. Consequently, all you need to do is measure the wavelength of the most redshifted component. Here's another spectrum, and in this spectrum, the arms are not as cleanly separated as in the previous one. But all you need to do is to find the most redshifted peak. It's not necessarily the brightest peak. It's the one that's farthest to the right. Then estimate, measure the location of that peak to 4 decimal places. Input that in these equations, and you'll have the speed of this special region relative to us. To that, you then have to add our motion along this line of sight. To calculate that, you begin with our motion around the center of the galaxy. We're traveling at about 220 kilometers per second. And this has been measured with respect to other galaxies in all directions around us. The component of this motion along the line of sight is 220 kilometers per second times, again, the sine of the galactic longitude. You can see that here. So the total motion of our special region is its Doppler motion plus 220 sine L. Once you do this for a variety of lines of sight and a variety of these special points, you'll have the galactic rotation curve. Now, let's take a look at our last section where we'll use these distances and velocities to determine the distribution of mass throughout the plane of the galaxy. To see how to do this, first consider the case of Earth orbiting the Sun. Earth's orbit around the Sun is almost perfectly circular, but this depends upon the mass of the Sun being the mass that it is. If the mass of the Sun were to suddenly drop to nothing, we would fly off in whatever direction we were headed at that time and at the same speed. If the mass of the Sun were to become suddenly much greater, we would again deviate from a circular orbit and spiral in towards the Sun. So the fact that we continue to orbit in a circle depends upon the mass of the Sun being the mass that it is. Or to turn this around, if you were orbiting something at a certain distance and at a certain speed, how much mass has to be there for you to be orbiting in a circular fashion? Well, this is something that Newton figured out, and it's given by this equation here. The mass interior to your orbit, and that's what it depends on. The mass interior to your orbit. Any mass exterior to your orbit, all those gravitational forces cancel out. So the mass interior to your orbit is equal to the velocity that you're orbiting squared times your distance from the center divided by Newton's constant. Now, you can solve this for velocity, which we've done here in the case of the solar system. In the case of the solar system, it doesn't really matter at what distance you're orbiting. The mass interior to your orbit is pretty much the same for all objects in orbit. And that's because in the solar system, all the mass is concentrated into the Sun. So in this case, the enclosed mass is just a constant, and so the numerator is a constant, but you're still dividing by distance in the denominator. So in this case, your velocity drops as 1 over the square root of the distance. And you can see that here in curve A, and this is what we call a Keplerian rotation curve. Things orbit faster, close to the center, slower, farther away. Such as Mercury, it orbits faster than Neptune. Now, this is not the only distribution of mass you can have. In many galaxies, the mass is not concentrated at the center, but instead spread throughout the disk. If you go twice as far out, you've enclosed twice as much mass. If you go 3 times as far out, you enclose 3 times as much mass. In this case, the enclosed mass is proportional to your distance from the center. So coming down here, if enclosed mass is proportional to distance from center, then that's going to cancel with distance from center in the denominator. In other words, you end up with a constant. So in this case, where the mass is distributed in this fashion, you end up with what we call a flat rotation curve. After you ramp up, then it stays flat for a great distance. So in this lab, you're going to take your distance measurements and your velocity measurements, plot the rotation curve, and determine whether our galaxy, if its mass is centrally concentrated or if it's distributed throughout the disk. Also, you can take these, and for each distance from the center that you probed, you can calculate how much mass is interior to that distance. In other words, you can weigh the galaxy. Okay, that is it for this overview video.